2022年10月31日，搭载着梦天实验舱的长征5B在海南文昌发射中心成功升空。之后的几天里，它将会与中国空间站进行对接，形成 T 字形的结构。那在它开始进行科学实验之前，你们有没有想过，如何才能将自己的科研设备或者太空望远镜放到中国空间站呢？这位科学家他在17年前就开始规划这件事情了，并且由他主导设计的第一代太空望远镜已经成功的在天宫2号中进行了科学任务的观测，还取得了不错的成绩。那第二代的设备呢，预计将会在2025年部署在空间站实验舱。那今天我们就要和这些幕后的科学家们聊聊中国空间站上的高能射线捕手天极望远镜。
So for what I understand, we will go up in one of these cargo ships that will be docked here at the end of the Tianhe module. So some astronauts will go and pick the detector, and they will translate the detector here, take a turn here, go here in Mengtian, open this door, and then with this robotic arm they will take it and translate it to here, and we will be installed here.
哦，对了，像是国内这些天文仪器呢，能找到的视频素材不多，所以我专门给这台望远镜建了个模，做了部小视频，一块儿来看一下吧。天极这台设备主要是观测宇宙中伽马射线暴及其偏振。在我们具体了解它的科学研究之前，我们先来看看如何从零建造一台望远镜，然后把它送入太空。
We wrote a paper about how to do this measurement properly, so we designed a detector, and then we proposed that detector in a paper, and I published this paper, and then we went to many places trying to sell it and to make it launch. So I went in Russia, I went with India. With India we went quite far. In the end they say no. Russia, they say okay, but you have to pay, and the price was too high. And we discussed also to put detector on the Iridium satellite. This didn't work also for, it was too expensive. I proposed it to European Space Agency, they were not interested. We proposed it to NASA, but you know, as Swiss people we cannot propose something to NASA, it should be American people. So I was kind of despair, and one day I received a mail from China, from Shangnan Sang, and he asked me many questions about the paper, details, you know, how is that really working? So I answered all these things, and we started to have conversation by email, and then he tell me, this is interesting. So he invited me to discuss that in China. So we went there, we had a meeting in a room where we discussed, but nothing was very precise at this time. And then, you know, we went 2-3 times, and then he said that probably there is a possibility to send it on the Tiangong 2 space lab, so, which is there. So that was very exciting. But then we had to start to discuss with the people how to adapt that, you know, about data transfer, about power, about temperature, insurance, that thing will not kill somebody.
前边 Nicholas 他提到了说寻找这些发射机会，他的唯一目标就是说发射不花钱，我去找一个机构能够帮我们免费送上天，那么我就在发射这个上边就没有成本，否则的话这个发射也会需要你自己付。
对，
然后发射上面是没有成本的，因为跟中国这个天宫2号实验室合作，发射成本没有，那么主要成本就在于就是把这个仪器造出来，
建造
这个仪器造出来，它的成本应该是大概是在几百万欧元。但他们提到了前期犯过一个错误，就是在做震动测试的时候，他们 给的800-900G 给的太高了，基本上就把这个仪器模拟这个发射过程中，你会这个有这个 shock， 然后它会模拟这个环境，然后把它给损坏了。后来就是重新花了一些钱，但总的成本来说，应该就是几百万欧元的一个小项目。所以这个也就是为什么当时那个双男联系这个Nikola，就是因为这个项目它的成本不高，而且很小型，就可以就是把它放在这个空间站，一般是后来的事嘛。当然，天宫2号是作为空间站的前期的一个探索性的一个项目，它不大，但是呢，这个项目就很小，就可以把它放在一个地方，很容易实现，不会占多少资源。但是呢，它做的科学呢又是非常有兴趣的，所以就是有这么多方面的优势啊。
你们会看到这台望远镜的形状有些特殊，像是可见光或者红外一类的望远镜呢，都由镜面来构成。但是 Polar 的主体呢，就是这些立柱，所以我们也把这类的望远镜呢称为探测器。在天文里，这种没有明确镜面的情况呢，还是很普遍的。比如像是研究中微子的探测器，整个设备呢有25根立柱，这里每个立柱呢都是一个探测器单元，它其中包括了碳纤维的外壳、8×8排列的塑料闪烁体、探测光信号的光电微增管和底部的处理器。当高能的伽马射线打到这些探测器上，就会发生康普顿散射，相对应的塑料闪烁体就会产生光，从而被底部的传感器记录下来。在发射升空之前，除了要做振动测试以外呢， Polar 还需要经过其他的一些测试及校正。
In the end, we were able to bring a detector in China. There we did a lot of tests also in Shanghai. And then we gave the detector to the people of the station, and they put it on top of the station. I was in Jushuan during this operation, and then we came back, and then there was the launch, so we went back to China for the launch. So we were able to see the launch of Tiangong 2 in space. That was really, and it's really emotional, because if anything goes wrong, you will lose several years of work. So, and then it was in space. Then we went to Beijing to switch on the thing. So that's also very because if the thing doesn't answer, but it immediately answer, and I think 2 days after we turn on the detector, we got the first GRB.
就前期会有一些对这个探测器的一些监控嘛，看它的状态如何啊，对它的一些数据进行一些评估啊，以及要对它上传一些指令去控制仪器的状态，进行标定啊。然后在前期这2-3个月的时候，我们还会经常跑到地面的这个到空间中心去值班，经常可能会大家换班，白天和晚上都会轮着来，然后去监控仪器的状态。所以前2-3个月都会进一些这个值班任务
啊，就是不光是收数据，你还能看到就是这个设备的，
对，你能实时监控到，在那个监控大厅，你能实时看到这个天宫2号，就是这个飞行器，它在这个它的位置，它在这个地球上的位置，以及当它路过地面的接收站的时候，数据就会下传，这个遥测数据，你就可以去通过一些可视软件去监控这个仪器的一些状态，它的一些工程参数什么的。
It worked for 6 months. After 6 months, we had a problem. We had a short circuit in the high voltage power supply. So it was still working, but not doing science. You cannot do science before in the high voltage, but we were still able to communicate with the detector. So we used that also to qualify the rest of the detector. So now we know that this detector can survive in space for several years. So when they proposed the Chinese space station, there was a call by the United Nations to make a detector on top of the station. We knew that before the call was given. Shuangnan Tsang tell us, we are preparing a call like that. So we were prepared. So as soon as this UN call went out, we were able to propose something to China, and we were selected. So we will be installed on the Ventian module, and in the meantime, here in Europe, we are preparing this Polar 2 detector, which will be bigger than Polar. it will be 4 times bigger. But in the meantime, also the technology changed, so we are able to have a better technology. So combining the 4 times bigger detector with a better technology, we want to have something which is 10 times better. And we hope it will last more than the 6 months that Polar. We have understood our mistake and we will not redo them again. So, but in 6 months, Polar had fantastic result. So yeah, we really look forward, and I think the science will be really exciting. So now I think the international community has understood that the science we are doing with this detector are super important and super interesting.
伽马射线暴简称 GRB 是宇宙中最极端最高能的射线。关于它的发现呢，其实还有一个小故事。在上世纪的60年代，美国为了监控苏联的核爆，发射了数颗名为 Vela 的太空卫星。在1967年7月，有2颗 Vela 卫星监测到一束闪爆，这束信号非常异常，不同于核武器所产生的信号。直到之后的几年里，人们才意识到这些异常的信号是来自于太空中的天体。那到底是何种天体可以产生如此极端的射线呢？关于 GRB 我们又了解多少呢？Polar 这台探测器又可以帮助我们做些什么呢？
So simply speaking, a gamma ray burst is just an enormous explosion in the sky that happens about once per day. So these things were first discovered by accident in the late 60s. But basically the first gamma ray sensitive detector that they put in the sky, they saw these enormous explosions. So naturally people became very interested in what these explosions are. And the more we learned about them, the more we understood how big these things are. Because, for example, in the beginning, people saw these things happen in random positions, random times, and they're very bright. So they figured they must be very close to us, because otherwise it wouldn't be so bright. And it turned out that they were not even in our solar system, they were not even in our galaxy, they were extragalactic, which implies that these things are incredibly powerful. So they are the brightest electromagnetic events in the universe since the Big Bang, so since its origin. And they occur in galaxies, and they can either come from the merger of 2 neutron stars, so 2 very compact objects that come together and explode and produce 2 very bright jets of emission. So it's not a spherical explosion, it's an explosion where you have 2 jets coming out. And if this jet points towards the Earth, we see it as a GRB. And what we see is initially a lot of gamma ray emission, which is why we call it a gamma ray burst. So it's a bright burst of mostly gamma rays, which last from tens of milliseconds to hundreds of seconds. They can be very short, they can be very long. So these short ones, they come from these neutron star mergers. The longer ones, we think, we're quite sure they come from something else, which is the death of a very massive star that explodes in some complex way, which is not a supernova, but a hypernova, so even more extreme than that. Now after this gamma ray emission fades, there is something called the afterglow. So these objects glow then on, which has been observed in radio, optical, X-ray, and this afterglow can go on for months. So that's what we see. So basically, since there's such extreme events, they're very interesting to study. It's not just the natural curiousness of what causes these enormous explosions, which is the natural thing, I think, why people started looking into this. But then, as time moved on, we realized that these things are basically, they exhibit physics at the extreme, like magnetic fields and gravitational fields and energies that are not accessible in the lab on Earth. So that's why it's very interesting to measure them, to study them, because you can learn things about physics, how it behaves in environments that we cannot reproduce in the lab on Earth. I think there's 2 main scientific achievements of Polar. So the first thing is that there were gamma ray burst polarization measurements before Polar, but most of them were wrong. They gave extreme results, like very high levels of polarization that even the theories couldn't explain. So they got a lot of attention, but unfortunately it turned out that many of them had issues. What we measure instead of Polar is that the polarization degree is relatively low. It's maybe unpolarized, it could be as much as 20, 30, but generally for the GRBs it's low. which makes it more difficult to measure because the lower signals, so it just gets more complicated. On top of that, the main thing that we learned is that it's not just low, but it could be that it's actually variable.
因为我们这个模式就是说，宽市场它在地球上绕的时候，就是比如说这个一个天宫2号的这个飞行器，它在随着地球绕的时候，它始终是保持了一面永远对着地上，另外一面永远对着这个外太空嘛。像 Polar 它是看外太空的这个现象，它就是永远对着太空。然后它在绕着地球转的时候，它是随机在调整轨道的，就一直保持这么一个状态，就是有一部分是对着升空的。那么在这个过程中呢，你除了可以捕获到这个随机发生的一些伽马射线暴的现象以外，你还可以看到这个，比如说太阳某一段时间会进入你的视野。太阳它是也有很多剧烈的活动的，会产生一些 X 射线，甚至到伽马射线的一些，比如太阳耀斑。这个太阳耀斑，事实上我们是预期能够看到一些太阳耀斑，然后去测它的偏振的。而事实上的话，就是我们在整个运行期间6个月期间看到了9例太阳耀斑，就跟其他的这些太阳监测器同时看到了一些耀发现象。但随着这个科技的进步呢，我们现在已经能够不光用我们的眼睛，我们会造一些人造的眼睛，比如说一些仪器，它可以帮助我们，比如说在地上或者在天上，我们都布局一些非常高精尖的一些仪器，比如说像我们有这个前面有 GPS 导航系统，然后后来现在中国有这个北斗的导航系统。当我们离开了这个地球，离开了太阳系到升空，我们再依赖这些导航的话，它的误差就会非常之大了，因为你离它们很远，这个导航的精度就达不到了。这个时候你就会想要利用一些这个宇宙当中的一些现象来进行导航，比如说脉冲星，我们刚才讲了，它们有这种周期性的信号，然后这个信号是，一般来说对一些毫秒脉冲星，这些信号是非常稳定有周期的，所以你可以用它们来作为，而且它们的位置在空中是不变的，你知道它就在那儿，然后它的信号是你对它的这个周期性是了解得非常好的，所以说你就可以把它们作为一个像宇宙中的灯塔来给你进行导航。然后像我们天极1号是看到这个一个叫蟹状星云脉冲星的，那它基本上是天上最亮的一个脉冲星，所以说就用它的信号来进行了一些定轨测试，就是我们在绕转地球转的时候，我们的轨道参数，尝试来利用这个天极1号对这个脉冲星的观测来确定我们的轨道。然后完成了这个测试，把这个定轨精度确定到大概是在10公里这样一个量级。可能我们对比现在我们已有的科技，比如在地面上导航，可能北斗能做到厘米级啊，但是这确实是不一样的一个概念，因为在深空中，这个10公里已经相当于是一个很好的一个精度了。
对，
因为你比如说你想要到达某一个星体，它们的尺度，我们到那儿的距离通常就是天文数字。比如说是多少光年啊，或者说它们的这个自身尺度是多少的公里啊，非常非常大的一个数字。所以你有这样一个精度，其实已经是非常够用了。你先从地球出发到那个位置，有这么一个精度，你能够大概到那个附近。到那个附近过后，你可以再想着切换到别的这种导航的方法，比如说你有一些光学的这种导航，你知道这个物体在那儿，你就朝那个方向去。
The nice thing about Polar 2 is that it will be on the China Space Station, where there's also a supercomputer involved. So we can actually not just see the gamma ray burst very quickly, we can then do some quick calculations on where it is in the sky, what the spectrum is, and hopefully within a few seconds of us detecting it, send the message automatically to ground and tell everybody that there's something interesting and you should look up there. So this is sort of a thing that comes for free, thanks to it being a very big detector and thanks to the China Space Station, that we also can make a big contribution to what is now known as multi-messenger astrophysics.
Okay, right. It's kind of an alarm.
Yes, so it's an alert system that's optical telescopes or everything on ground can repoint quickly and look that there's.
好的，这就是这期视频的内容啦。如果你喜欢物理，喜欢天文，别忘了加关注。我们下期再见吧，拜拜。